Many years from now. Hello, Mr. Huang, are you there? Recording. Okay, good morning, everyone. So welcome to week 2. Week 1 was long and arduous. We did about maybe 3 weeks worth of Comp 330 material in 4 days. So I put up assignment 2, which has actually some more questions on last week's material, just so that you've had more time to think about it. But then also a few questions on this week's material. Everything I'm doing this week is new, meaning I've never taught it in Comp 330 before. So you guys signed up for an enriched version. Well, this is the enrichment. So we're going to do new topics. And let me just check the course website. I've actually thought about it as I was preparing the lecture for today, and I realized things were not quite in the right order. So I put up a new schedule. I don't know if anybody looked at it yet, but I updated it last night. And now the lecture schedule for week 2 reads like this. Today, May 11th, we will do Omega-automata, not temporal logic. We'll do temporal logic tomorrow. So Omega-automata wasn't on the original list, but it's a natural thing to do right after automata. And it makes more sense to do temporal logic after Omega-automata. And then bisimulation got pushed to the 3rd lecture. And on the 4th lecture, we'll do learning automata, which probably will only take half the time. So then we'll just chat for the other half. Or if the spirit moves me, I will do epistemic logic. The lecture on bisimulation will include a little bit of lattice theory. So week 3 has been also slightly changed. I realized I wanted you to learn about reductions and things like that earlier rather than in the very last week, because this is such a crucial topic. So I moved lambda calculus from the 3rd week to the 4th week so that we could do reductions, PCP, val comps, and things like that early on. The topic on logic and unsolvability and the arithmetic hierarchy stays where it is. Then we do lambda calculus, then fixed point theory, and finally Gödel's and Tarski's theorems. So assignment 2 is due on the 18th. I'll give you assignment 3 on the 18th, and it'll be due on the 25th. And now I'm in a bit of a quandary. I'm thinking I'll give you assignment 4 on the 25th and have it due just in a few days. So maybe on the 28th. And it won't have, it'll be mostly a reprise of week 3 material and maybe just a little bit about logic and unsolvability and the arithmetic hierarchy. The reason for that is, I'm not 100% sure of this, but the reason for that is the final exam, which, as I told you before, cannot be an oral. It has to be a take-home. So maybe I should ask you, would you like to have the final exam distributed on the 29th, Friday, and have it done over the weekend, or do you want to do it the following week?
Someone said weekend.
Justine is for weekend.
There's 2 weekends. I say weekend too, so 3. 4 weekends, 5 weekends. Okay.
Okay, so I'll do it on, okay. Yeah. And Rosie is smiling enigmatically, so I don't know what she wants. You don't care. No matter when it is, you will kill it, right? Okay. Yeah, final exam I decided will be a take home. It should be easy. It should be the kind of exam you can probably do in 3 hours, or given how smart you guys seem to be, 2 hours. And it won't be like those killer homework questions. So question assignment 1 had 2 killer questions, 7 and 10. So some people emailed me last night saying, I think I can prove that 10 is impossible. Sorry, it's not impossible. I just because you couldn't do it is not a proof of impossibility. Okay, good. Enough chit chat. Let's get on with the show. So today, Omega-automata. Let me close this window. Yeah, let me do that. And here we are. Okay, so there are nice lecture notes one can find here and there on the web on Omega-automata. There's a nice book. So I used to teach this material in Comp 525. I've never before taught it to Comp 330, but then you guys are not ordinary Comp 330 students, right? You are specially selected elite students. So we have considered languages over an alphabet sigma. We defined the set sigma star to be the collection of finite words. And we defined the word language to just mean subset of sigma star. Now, we're going to do something new. We're going to introduce sigma omega, which is the set of infinite words over sigma. Okay, infinite words. So remember before in sigma star, each individual word was finite. The number of words, of course, in sigma star is infinite unless sigma happens to be the empty alphabet. So even if sigma is a singleton alphabet, sigma star is infinite. Sigma omega, on the other hand, is the collection of infinite words. And it's a bit peculiar. Over a one-letter alphabet, sigma omega is in fact a singleton because there's only one word, only one infinite word you can make with one letter. It's A going all the way to infinity. But over two letters, sigma omega is not just infinite, it's actually uncountable. All right. So sigma star is infinite but countable. Sigma omega is uncountable. I'm also going to use some more notation. I'll use sigma infinity to stand for sigma star union sigma omega. Okay, so that's the collection of finite and infinite words or finite and infinite strings. So everybody is comfortable with the concept of an infinite string? Not mystifying to anyone? Very good. So it's simply a string that goes on forever. The string itself is countable. So that means the positions in the string can be indexed by the integers. So positions in the string can be indexed by natural numbers. With a bad N. Okay, so I will write if alpha is in sigma omega, alpha sub n is the letter at position n. And by the way, we always start counting the positions from 0. So the first one is alpha 0, then alpha 1, alpha 2, and so forth. There is a natural order structure on sigma infinity. So we will say alpha is less than beta if alpha is a prefix of beta. So that means you've got some string and some initial portion of it is alpha, but then it goes on, possibly forever. And this is beta. So then we'll say alpha is less than beta. Now, if alpha is in, so you remember, notice that this order is defined when you have both finite and infinite strings together. If I have one infinite string, it cannot be less than a different infinite string. Okay, so in fact, the infinite strings are not just countable, but they have the order type of the first countable ordinal, first infinite ordinal. Okay, so is everybody clear about this? So for example, AAB is a prefix of AABAB. AAB is also a prefix of AAB, AAB, AAA, da 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 forever. Again, how do we know? We see this prefix sitting there. Okay, is the order structure clear? I'm going to make some remarks in red. So this, when I write things in red, it means you don't have to understand it. It's a additional remark made for the benefit of those honors math CS people who are so fond of topology. Okay, so additional remarks.
We have a question.
Yeah, sure.
Does that mean that infinite strings are not prefixes of themselves?
They are prefixes of themselves. I said it cannot be the prefix of a different infinite string. And if they were not prefixes of themselves, then it wouldn't be a partial order because reflexivity is part of the definition of partial order. But good question. Additional remark. So we can define a metric on sigma star by saying the distance between two strings x and y. I tend to use letters like x, y, v, w when I'm talking about sigma star, and Greek letters when I'm talking about sigma infinity or sigma omega. But that's just a notational convention. So I'm saying the distance between two strings is 2 to the minus n, where n is the first position where xn is not equal to yn. If xn is actually a prefix, if x is a prefix of y, then we'll say they differ when we see that x has ended and y has not. Okay, so we'll say that position is where they first differed. So the idea here is that if you have two strings and for a long time they look the same, and then finally after a great going out a long way, you notice that they're not in fact the same, then we'll say they're very close. Whereas if they differ right up front, then we'll say, oh, they're very far apart. Okay, so this is a metric. So you can easily check the metric axioms. In fact, this defines an ultrametric.
We have another question from Maria. She
Yeah,
asked if the metric is defined in sigma to infinity.
just 1 second.
Yeah.
Yeah, sorry, Maria, what was your question?
That we can define the metric on sigma infinity, not only sigma star.
Exactly. So sigma infinity is the Cauchy completion
Oh,
of sigma star. And the metric naturally extends to sigma infinity. Does everybody know what ultrametric means? Well, does everybody who cares know what ultrametric means? So if you remember, the metric axiom is one of the axioms is the triangle inequality. But for ultrametrics, you have a much stronger axiom which says dxy is less than max of dxz dyz. So this is called the ultrametric inequality, and it has weird consequences for the geometry of ultrametric spaces. So all triangles have to be isosceles. All open balls are closed. And you can't have two balls that kind of intersect like that. They're either disjoint or one is inside the other. So a bit hard to visualize from our usual notions of metric geometry. Okay, let me draw a line under all this, because those of you who don't know these things are probably wondering what the heck I'm talking about. And anyway, these are not important for the class, just for fun. Right, so let's get back to the main the main issue. Why the hell am I talking about infinite strings anyway? Who cares? Is this just like mathematicians going wild? And so the answer is no. They're extremely important for the verification of reactive systems, because you often define reactive systems as things that are running forever. So when we talk about normal programs, you have this idea, you feed in some input, it does some computation, and then it outputs it and terminates. That's a normal program. But for reactive programs, like an operating system or anything for which you're pushing buttons and waiting for responses, or a server that's just sitting there running forever, responding to client requests, these are all what are called reactive systems, and they're designed to run forever, right? Of course, people will tell me, well, the age of the universe is not infinite. I'm not sure how you know that, but anyway, people do tell me stuff like that, and I say, yes, well, true, but we don't design an operating system with the end of life programmed into it. We tend to program it as if it is running forever. So the reasoning about it and the correctness aspects of these kinds of programs have to talk about infinite computations. And now to verify properties, is this thing behaving well? We would like to say things like, well, it always does this, or eventually that happens, and so on. So you see these words always and eventually. This will be part of the temporal logic that I'll introduce later. So that's the logic for talking about these things. But right now, I'm trying to motivate the use of these infinite sequences is highly enriched nowadays by the requirements of practical verification. So despite the apparent abstract nature of what I'm saying, it's indeed highly applicable stuff. I am not going to talk about the applications and model checking and all the algorithms that are based on Omega-automata. That is something I would teach in my formal verification class if I ever get to teach it. But for now, I just want to introduce you to the Omega-automata analog of everything we did last week. Okay, so first of all, how are we going to talk about these things? There are uncountably many infinite sequences. So there are like Aleph 2 languages one could have if you just define them to be subsets of sigma omega. So we need to get a handle on things that we can actually describe in a finite way. And this leads me to this new topic, which is called omega regular expressions. Omega regular expressions. So I'll say regular expression. When I say regular expression, I mean old-fashioned regular expression defining regular subsets of sigma star. And we totally understand regular expressions. They exactly correspond to regular languages, which are defined as things recognizable by DFAs. We proved that DFAs are equivalent to NFAs, and they're further equivalent to NFAs with epsilon moves. We will find that when we try to explore these concepts in the omega case, a lot of these things break down in quite interesting ways, in fact. Okay, omega regular expressions. So this is going to be, so unlike what we did before, which was to start with automata and then introduce regular expressions and say, regular expressions exactly describe the things recognized by automata. We're going to start with omega regular expressions and later on introduce an automaton model to recognize these omega regular languages. So everybody with me? Okay, so omega regular expressions. So let E be a regular expression. And as I said, when I just say regular expression, I mean a regular expression. Then, if E is a regular expression, and just for simplicity, I'm always going to emphasize epsilon is not in the language of E. You can develop all this with epsilon in the language of E, but then every definition ends up with a lot of exceptions, like except when epsilon is there, or if this is not epsilon, then you have to. So I'm just going to say, you know what, epsilon is never there in our languages. Just it gets some irritating cases out of the way. So please don't jump up and say, what will happen if epsilon is in the language? Yeah, you know what, I don't care. So let's deal with regular expressions, and we'll always understand that we've chosen the regular expressions in such a way that epsilon is not in the language. E omega is an omega regular expression and it is defined as the set of infinite words like this. Every WI belongs to the language of E. So actually I should say the language of E omega. And just to emphasize, I'll put a little subscript. So L omega of F means the omega language defined by the omega regular expression F. So it's clear what this thing means. E omega means take infinitely many words from the language defined by E and just stick them together. Since none of them are epsilon, you will actually get something that's infinitely long. Okay, so this is a kind of a nice extension. So what are the kinds of things I can write? I can say, you know what, A star B B B A infinity. Sorry. A omega is an example of an infinite string. It's also an infinite regular expression. Okay, and it means what you think. Maybe there's some A's in front, maybe not. then there are 3 B's, and then there's an infinite sequence of A's. Okay. So you can see, yeah, we're allowing infinite strings. We're allowing subsets of infinite strings, but we're going to kind of look at things that have regular or repetitive patterns. So formal definition of an omega regular expression. Let EI be regular expressions such that epsilon is not in the language of any of the EI, and Fi be um, mm, be also regular expressions such that epsilon is not in the language of the Fi. Actually, this is important. This is not important. I could have, in fact, let me scratch that one. This is the important one. Okay, so these are regular expressions. Fi's are regular expressions, and I've insisted that epsilon is not in the language of any of these Fi's. Then E1, F1, omega plus E2, F2, omega plus En, Fn, omega is a general omega regular expression.
We have a question in the chat.
Yeah.
What's the regular expression that generates that omega regular expression?
Sorry?
What's the regular expression that generates that omega regular expression? I think there's a typo. Maybe not. For A star B B B A infinity.
Uh-huh. So, okay, good. So of course I'm allowed n of these, but I could have just one if I wanted. So this thing, A star B B B, that's my E, and that's my F.
She says
Is
thanks.
that what you were asking? Okay. So also note, if I have just E omega, then E omega is always the same as E dot E omega. So E omega is also a regular expression. Sorry, an omega regular expression. Let me explain a little bit about concatenating omega strings. Supposing alpha and beta are both in sigma omega, alpha dot beta is just equal to alpha. Because basically alpha fills up all your space. There's nothing you can put on the right-hand side of it. Normally, when we define concatenation, we say when the first string ends, then you start the second string, but the first string never ends. So you can write this if you want, but it's going to be the same as alpha. Actually, if alpha is in sigma omega and beta is anything in sigma infinity, alpha dot beta is just alpha. Oops. If alpha is in sigma star, and beta is in sigma infinity, then alpha dot beta has the meaning you would expect. Okay, so there we are. We have a class of languages. An omega language, i.e. just a subset of sigma omega, is said to be omega regular if it is defined by some omega regular expression. Okay. This omega reg exp may not be unique. Okay. So dot is concatenation. And extended to concatenation of languages from concatenation of strings. Plus is, of course, union. And this is infinite repetition. All right. And now we're going to talk about Omega-automata. So Omega-automata are going to be tricky things. So remember how we defined, or well, superficially it's going to look the same. Okay, so what does that mean? So we'll call these things, there are many, many different kinds of Omega-automata. We're going to look at a specific one, specifically what are called non-deterministic Bucci automata. Bucci was a Swiss mathematician and logician who proved fundamental things. He introduced omega automata. So these are sometimes called NBA. So I'll use NBA for non-deterministic Bucci automata and FA for non-deterministic finite automata. Now these automata are also going to be finite state. So let's write down the definition. It's got a set of states. There's an alphabet. There's a transition relation. There is a set of start states and a set of final states. And in this case, it's convenient to start with the non-deterministic case and study the deterministic case much later. So deterministic automata we'll study after the break. All the intuitions you developed, not all, but nearly all, are going to break. So yes, so the fundamental concept is going to be NBA, non-deterministic Bucci automata. And I think none of these need explaining, except let me spell out how delta works. It is a transition relation. So you're in a state and you read a letter and you can go to a set of possible next states, and that set might be empty. So the automaton might jam. And if you're in a jammed state and there's no transition for you, boom, you're rejecting. And otherwise you have accept states as before. And just from a point of view of notation, we have this kind of thing, right? Sigma prime belongs to delta SA. So this says, oh, can everybody still see me? I'm getting messages claiming internet connection is unstable. Okay, we will write this as S A S prime. And this arrow notation means if you're in S and you read an A, you could end up, not you must end up, but you could end up in S prime. So these are equivalent notations. It's just that I actually like this because it kind of shows you the things moving around. So these are actually a notation that was invented by my former master's supervisor, Robert Keller, and this is called label transition systems. Okay, now the thing you're probably wondering is these things are going to read omega words, infinite words. So how are they going to accept? Obviously, you can't say in the last state when you finish the word. So here's the intuition. You have some accept states and some other states that are possibly not accept states. And as you're reading a word, you're going through the machine, jumping around from state to state in the manner dictated by delta. Of course, delta is non-deterministic, so you may have some choices, but given a word, there's many possible paths of executions. Now let's look at one of these possible paths of execution. It's called a run. So let me define a run. Given a word sigma in sigma omega, a run of sigma in A is an infinite sequence of states I'll write this Q0, Q1, Q2, Q3, such that little q0 is one of your start states, and for every I, qi takes sigma I to qi plus 1, where sigma I is the letter at position I of sigma. Okay, so that's called a run. Because it's a non-deterministic automaton, the same word can have many distinct runs because you get to make choices. So here's the intuition. You take a word, it has a run through the machine, possibly many, but look at one of these runs. Every time you reach an accept state, you ring a bell. Bang, 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 you ring the bell. Okay, and now you accept if you ring the bell infinitely often. So the acceptance condition is not where do you end up, but did I hit an accept state infinitely often? So we will define So let me introduce some notation for this run. We'll call R a run, and we'll say inf R is the set of Q such that Q occurs infinitely often. In R. And we will say a run is accepting if it hits an accept state infinitely often. So this means inf R intersection F is not empty. So you might say, does it have to hit one specific accept state, or can it hit, sometimes this one, sometimes that one? Doesn't make a difference, because if you've hit an accept state infinitely often, there are only finitely many accept states. So one specific one of them had to be hit infinitely often. This is the infinitary version of the pigeonhole principle. If you're trying to put infinitely many pigeons in finitely many holes, one of those holes is going to get infinitely many pigeons. Okay, so it doesn't matter exactly how you define it. And we will just exploit this. So if there are no accept states, then, sorry. We say a word is accepted by A if that word has some accepting run. So this is just like in NFA. It doesn't matter if bad choices lead you not to an accept state. So here also, it doesn't matter if there are bad choices that lead you to a non-accepting run. As long as there's one accepting run, you accept the word. And it doesn't matter if there's 1 or 17 or infinitely many. Okay. So,
yeah. F must be a finite subset of S?
Well, did I say S or Q? Q, yes. Well, Q itself is finite.
S2, right?
Where's S?
I don't see it either.
And F is obviously a subset of Q. Q0 is also a subset of Q, so these are also all finite sets.
They meant Q and they said thank you. Oh, and then Maria asked, would it be possible to think that an accepted run is eventually periodic, or is this just a special case?
I should bribe Maria. These are great questions, Maria, but I'm coming to this. This is exactly a crucial point. Short answer is yes, but in some sense. In some sense, okay? And we will come to that when I prove the grand theorem that relates omega regular languages to non-deterministic Bucci automata. But perhaps an example. So, example. Right. So here's our start state. We still use the same notational conventions. A little arrow coming from nowhere indicates this is where you start from. These are non-deterministic, so there could be multiple start states, but this example has only one. And it's a 3-letter alphabet, ABC, so sigma is ABC. So there are 3 states. And I'm going to ask you to tell me the language. Okay, so C just spins here. A takes you there. B takes you here. This is the accept state. Of course, there can be multiple accept states, but this example has only one. And then B brings you back. So C omega is not accepted because that will just spin here. It's never accepting. It's just spinning in Q1. It's never hitting an accept state. So what's something that is accepted? Okay, A B omega is accepted. Right? A B B omega is accepted. So anybody want to tell me what's the omega regular expression describing what's accepted?
Maria asked if the arrow below should be A.
No, should be B.
Omar said C star, A, B star, all of that in parentheses to omega.
C star, A B star.
The B is starred, yeah. And all of that omega. Sorry, with the C.
Oh, okay. Like that.
Then there's some variance.
Well, this is wrong.
Then there is C star, A, B, B star, all of what I've just said to omega.
C star, A B.
And then another B star,
Yeah.
all of that to omega.
I think this is also wrong. But good tries. Why is this wrong? This is wrong for an easy reason. Because this includes, for example, CA omega, which has no B's. And you can see there's no way you're getting to Q3 without a B. So this is definitely not right. So this one, I'll leave you to ponder. But the omega language of this automaton is C star, A, B, B plus. By the way, when we write plus, like B plus, this means B, B star. So star means 0 or more repetitions. B plus means at least 1 or more. Okay, so B plus, so you better have at least one B there. And you need that one B to bring you back. And that's why this is not marked with an A, but with a B. And then B, C star, A, B. This is the one that brings you back. This one, then you cycle for a bit, then an A and a B. And this can be repeated. And so you see, Maria, this actually is described by some kind of omega regular expression, but it's not exactly periodic because I can make different choices. So I can say first one B and then one of those, and then two Bs and then one of those, and then three Bs and then one of those. So that's not periodic, but it's got a kind of periodicity aspect to it for sure. Okay. So just to give you an example, we often use these omega regular languages to specify properties. So for example, you're writing down a formal specification for how traffic lights work. We'd like to say infinitely often the light turns green in your direction. Yes, so you can write down an omega regular expression that states that fact. And so these are the kinds of properties that people use to specify, especially when they're writing concurrent and reactive programs. So they want to say things like, every time I make a request, eventually this thing is request is granted. You want to be sure that your server protocol actually satisfies a property like that. So for all these kinds of things, you do want to talk about infinite executions. Okay, how are we doing? My God, almost an hour. Better get going. So the theorem. NBAs accept exactly the omega regular languages. By the way, for all you topology freaks out there, we put a metric on this on sigma infinity, which of course we can restrict to sigma omega. And I'll just ask you a question. What kind of subset of this topological space are omega regular languages? They're not open, they're not closed, but they are something. Okay. So let's prove this. So the basic proof idea is by, so two things we have to do, right? We have to show that anything that's described by an omega regular language can be accepted by a Bucci automaton. And we're going to do that proof by induction on the structure of a regular expression. So the regular expressions were defined inductively, omega regular expressions. So basically we're going to show that if I have an NFA and an NBA and I concatenate them, that's something that can be recognized by a Bucci automaton. If I have two things that can be recognized by Bucci automaton, I take the plus, that thing can be recognized by a Bucci automaton. And if I have some ordinary regular language described or recognized by an NFA, then its omega iterate can be recognized by an appropriate NBA. So if I prove those three facts, it then follows by induction on the structure of regular expressions that anything described by a regular expression is accepted by some Bucci automaton. So is the plan clear? That's of course only one direction. So let's do it. So given two Bucci automata, Qi, so I will be either one or two, so I'm writing two of them at once. So I've got two Bucci automata with disjoint state spaces. That's just for sanity. I mean, if they were not disjoint, you can rename them. And now I'm going to define a new, automaton called A1 plus A2. This is just the name of the automaton. And it's going to have as its state space Q1 union Q2. Since these were both finite sets, obviously their union is also finite. Same alphabet. It's going to have a transition function that I'll define in a minute. The start states are just the start states of either one, and the accept states are just the union of the accept states. And the transition relation. So basically, you can choose which machine you're going to start in, and thereafter you either follow the transitions of that machine. sorry, thereafter you follow the transitions of that machine. So you have the option of starting in a start state of A1 or in a start state of A2, and then which, depending on that initial choice, you will follow the transitions of that machine. So delta QA is simply delta I QA if this Q is in QI. That's all. So you just said, somehow I've magically guessed from my union which language it's in, and I'll pick the right machine. And of course, this has to work. So this is easy. So the language of A1 plus A2 is easily seen to be the union of the languages of A1 and A2. Okay. Now I have to do the star case. Okay, so the star case is a bit tricky. So we assume, so this is just part one. So now we assume okay. So we have an NFA for F. So remember, F is an ordinary regular expression. So it has an NFA, and we'll make an assumption. We assume all the initial states are non-accepting. So that means we're assuming that Q0 intersection F is empty. And there are no incoming transitions. To any state in Q0. So these Q0 states are start states. There's no transition coming into one of those Q0 states, and none of them are accept states. So of course, this is kind of forced on you because if any of those Q0 states were start states, epsilon would be in the language. And you might say, well, this won't allow me to have epsilon in the language. Yes, that's true. That's what we want anyway. But you might say, but it's limiting me in other ways. How do I know that every automaton can be put in that form? So the point is, if your if your NFA does not satisfy these assumptions, we can modify it so that it does and defines the same language. And I'm not going to spell out how that's done, but here's the idea. You want to fix it up so that it has this property. You define a brand new, unique new start state called Q new. Every time you see a transition, from one of the original start states to a state with a certain letter, you put a transition from Q new to that state. You make Q new the sole accept state. And thereafter you leave everything untouched. So you can easily check that this works as advertised. All right. Okay, so we are given A, which is an NFA for L. With Q0 intersection F equals empty. And no incoming transitions into Q0. Okay, so I'm going to define an NBA A prime. It's going to have the same state space, the same sigma, a new transition function, a new set of start states, and a new set of final states. Okay, and the idea is the omega language of A prime is going to be the language of A repeated. So the only important thing I need to tell you is what's delta prime. So delta prime, you're in a state, you see the state space has not changed. You're in a state, you're reading a letter, and you do one of two things. It's just going to be the same as delta QA if delta QA intersection F is equal to the empty set, or delta QA union Q0 otherwise. So basically, if you're going to hit an accept state, we'll say, oh, in that case, I'm going to put you back in a start state so that you can restart and read another word. Because what this thing has to do is keep recognizing infinitely many of these words that come from the original non-deterministic finite automaton. The start states of the new machine are the same as the start states of the old machine, but these are now going to match with the new accept states of the new machine. The new machine certainly does not have the properties that we demanded of the NFA. In fact, here the final states and the accept states are exactly the same. And basically, that's because I'm going to say every time you finish a word, I'm going to make you restart because there's always another word to read. And here now you see the importance of why the original guy better not have Q0 have any accept states, because I want to make sure that this restart happens when you hit an accept state. Okay, and when do I do that restart? Exactly when there is some possible accept state that you could be hitting in the original NFA. So the fact that this works is not difficult to see. So maybe I will show you an example of how an NFA gets modified to an appropriate NBA. So here's an example. So here's our NFA. It's got just two states. This is the start state. And this is the accept state. And what's the language of this machine? It's just A star B. This is, of course, an NFA. Now you see this violates the thing we had, no incoming transitions. No incoming transitions to the start state. So what we're going to do, we're going to define a new start state called Q new. We're going to look at the old start state. I'm sorry, this was Q0, wasn't it? And this was Q1. Okay. So of course we had the transitions there and there. And now it's not a problem because this guy is no longer a start state, but every time we saw any kind of transition from Q0 to something, we have to put transitions from Q new to that state. So Q0 has a transition on A to itself, so Q new needs a transition like this. And Q0 also had a transition to Q1, so Q new also needs a transition to Q1. So that's the modified NFA, and it obviously recognizes the same language, right? The reason it recognizes things with no A's is because I have a direct jump like this on a B, but if you want to read some A's, you're free to do so. Okay, so it's the same language, A star B. And now, what does the NBA look like? So the NBA says, oh, the old start state becomes an accept state. We have to put in all the transitions that were there before. So these were all the old transitions. And now we said, hey, every time this guy is hitting an accept state, like here or here, we have to put a return on the same label So here's an NBA, and its language is exactly A star B omega. A star. So this forces you to hit this accept state, but of course, as soon as you hit this accept state with a B, you get to come back. Okay, so if it's just A star and a single B, you can come here. If there are no A's, then you can just go directly there and back. So this illustrates the process of modifying an NFA. First, you modify it so that it has the desired properties recognizing the same language, and then you cook up the NBA. The argument is basically you look at the accepted runs of this thing and you see that you can always break it up into words that are recognized by the NFA. And finally, I won't formalize this too much, but case 3 is you have this kind of situation. So you have an NFA And then you have an NBA for F omega. And what you do is where you had accept states there, you hook it up to the start state here. And thereby you see, first you recognize something in the language of E, and here you recognize something in the language of F. And this is already an NBA to recognize that. So all the cycling that needs to be done will happen here. Okay, and you can formalize it rather straightforwardly. So this completes half the theorem, not the whole theorem. So this shows that any language defined by an omega regexp can be recognized by an NBA. So other direction. We have to show that if I've got a language that's accepted by a Bucci automaton, I can write down a regex for it or an omega regex for it. So suppose we have an NBA. So now I have to produce a omega regex for you. So fix any two states, say Q and P in Q. Okay, just pick any two. We're going to do this for all pairs. All right. So I'm going to define a new NFA, which I'll call QP, A sub QP, and it's going to be defined to have the same state space, the same alphabet, the same transitions, but I'm going to say you start in Q and nowhere else, and the only accept state is P. And this is going to be an NFA. So this is not meant to be reading omega words. This is meant to be reading ordinary words. So what is the language of this thing? We'll call this LQP for short. And it's precisely the set of words in sigma star. Remember, we're reading this as an NFA, such that when you run delta star, starting in Q on the word W, you end up in P. Non-deterministic, so it's not equal to. You'll end up in some set of states, but P will be one of them. So these are words, precisely the ones that take you from Q to P. Okay, so everybody clear about this construction? Now consider an accepted word, sigma, of the omega language of the original NBA. So what does this look like? It's accepting run has this structure. There's some Q0, Q1, Q2. Okay. This is an infinite sequence. Of course, there's only finitely many different states. You're going to be hitting the same state over and over again. So there has to be some Q in F which appears infinitely often. Sorry, that's not correct. That appears infinitely often. Okay, so call that thing Q, and let's look at sigma. So it has some initial word, and that word has to have hit Q. And we started out in Q0. So this belongs to the language L Q0Q, where Q0 is some start state. So we've fixed this Q as this one state that we know that appears infinitely often and is an accept state. Then we look at the next word and we see, well, this started in Q because that's where the last word ended, and it hit Q again. So this keeps going on. Aha. We know that all these WI are non-empty. So any sigma that can be expressed like this has an accepting run. And anything that has an accepting run has to have this structure. So now we can say the omega language of the automaton is just, you look at all the possible start states, you look at all the possible final states, and you look at L Q0 Q dot L Q Q with epsilon removed, and you omega it. So these unions, of course, in the notation of omega regular expressions, can just be written as pluses. These things come from NFAs, so they can certainly be written as regular expressions. So this is exactly the format of an omega regular expression. So anything recognized by an NBA is described by an omega regular expression. So this is our theorem. So this is Kleini's theorem for omega languages. Okay, let's take a short break till 12:10, and then we will do some properties of omega languages. Darn. Okay, well, is it recording now? So it shows on your screen that I'm recording or not? Oh, because you're the co-host, you can see that.
Even not co-host, you can see it.
I see. Last. Oh, well. But I guess these examples are in the notes. So when I upload the PDF of the notes, they'll see it. But anyway, we're now coming to the exciting bit. Deterministic Wuxi automata These are the same as DFA with the Bucci notion of acceptance. Right? So let's look at one more example automaton. So this is an NBA. Okay, so this is an NBA. You can see plainly at Q0, we have two different B transitions. So that's certainly non-deterministic. Okay, I'm going to ask you one more time. What's the language of this? What's the omega language of this automaton?
We got A plus B omega. A plus B is in parenthesis. And then B omega. No, sorry, my bad. I will restart that. Between parentheses, A plus B to star, and then B omega.
Very good. Exactly right. So you might say, gosh, we proved that NFA and DFA were totally equivalent. We could take the subsets of an NFA, and because an NFA has only finitely many states, the power set is also finite. It might be an exponential blow up, but it's still finite, and you can now track all the possibilities, blah, 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 blah. Surely something like that should work for Bucci automata. The answer is no, it's not true. So there is no deterministic Bucci automaton that can recognize the above language. In fact, this is an important point, so I'll call it a theorem. So I'm not going to use topology or convergence, but you can see this proof is all about topology and convergence. Okay, so this is one major dramatic difference between the theory of ordinary finite automata and omega automata. It's what makes omega automata much trickier. Okay, let's go. All right. Suppose we have a DBA. For this language. Okay. We can define delta star as usual. On the underlying DFA. Okay, so remember a DBA and a DFA look Go away, Siri.
Just a moment.
Shut up, Siri. You didn't get that? Shut up, Siri. Go away. Thank you. Okay. We can define delta star as usual or on the underlying DFA, because remember, underlying a deterministic Bucci automaton is an ordinary DFA. Okay. So consider the word. What's the magic incantation to stop Siri popping up? Is it shut up, Siri? Consider the word. B omega, which belongs to A plus B star B omega. Yeah, B omega is a possibility because I can simply say, I'm going to take this thing 0 times and go right to the B omega. Or I can take, this B 17 times and then take omega times from B omega. So everybody agrees that B omega is in the language, yes? Now, the crucial thing about deterministic machine is, if I specify a word, there's a unique path. There are no choices. So I can be sure that in every run, in fact, there's only one run for a word. So this is exactly what doesn't happen in an NFA, and this is what makes the present argument fly. Okay, so since B omega is accepted, we must hit an accept state at some point. Obviously, actually, we have to hit it infinitely many times. But anyway, at some point, we hit an accept state for the first time, or I don't even care if it's the first time. I know at some point I do hit an accept state. So P to the N1, so delta star Q0, B to the N1 is an accept state. Okay, so let's take B to the N1, A, P omega. So this is also in my language, right? So this has to hit an accept state again after reading A. Agreed? Because this thing has to hit an accept state infinitely often. So after the A, you can't just say, I've done my accept states. No, you have to keep hitting accept states eventually. So after reading that A, you must hit an accept state again. So say B to the N1A, B to the N2 takes you to an accept state. Okay, now consider, whoops, this should be N1. B to the N1, A, B to the N2, A, B omega. This is in the language, right? This is in the language, right? Because only finitely many A's in the language said, yeah, any finite number of A's is okay. Can't have infinitely many A's. Must have finite number of A's, but any number is fine. So you see what's happening is some kind of limit process is going to screw us. So this is in the language. And so this must hit an accept state. So we go on like that. B to the N1, A, B to the N2, A, B to the N3, A, B omega is in the language. So we get a whole chain like this. And we know that after all that finitely many A's, you must be hitting accept states again and again. Okay. So, continuing this process, for every I in the natural numbers, there exists n1 up to ni, also in the natural numbers, such that delta star q0 b to the n1 a, b to the n2 a, b to the ni a, b omega takes you to an accept state. But there are only finitely many accept states. So at some point, I have to hit the same accept state twice. I can't be hitting new accept states all the time because I'm going to run out of them. So I have to hit the same accept state twice. Getting excited and forgetting words. Have to hit the same accept state twice. In other words, there exists I, j with I strictly less than j, such that delta star q0 bn1 a bn2 a da 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 bni a b, sorry, now I'm just talking about this thing as a DFA. No, sorry, I got the A in the wrong place. This side, yeah. So there has to be some situation like this, where after reading a certain number of A's, you hit an accept state. Now, it's a deterministic machine. So it's not like this thing can make different choices. It has to follow this path once you've laid out a word. And that's, of course, the crucial part of our proof. So if this is happening, then in the NBA, remember the NBA is actually the same machine. We just have a different notion of what it means to accept. B to the N1, A, da 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 da, A, B to the Ni, A, B to the Ni plus 1, A, B to the Nj, omega has an accepting run. But this is a contradiction, because this has infinitely many A's. Isn't this a topological argument secretly hiding there somewhere? But anyway, this proves that NBA are strictly more expressive than DBA. So you might be interested in knowing what's exactly the difference. What's special about the languages that are recognized by deterministic Omega-automata? So what property are NBAs violating that DBAs are forced to follow? And this is in fact a limit property. Okay, so let alpha in sigma omega, and we define alpha cutoff at n to be a finite word to be the length n finite prefix. Okay, so with the vertical line, n means I took my infinite word and cut it off at letter n. So that's now an ordinary finite word in sigma star. And now I'm going to define what's called the limit closure. So take some set of words in sigma star. These are our good old-fashioned friendly finite words that we are fond of from last week. We define W with an arrow on top, so it looks a bit like vector. So it's this set of omega words such that there exists infinitely many n in the natural numbers such that alpha cutoff at n belongs to W. Okay, so it's called a limit language. So here's what's happening. You've got some ordinary regular language. Actually, I didn't even say it was a regular language, but I have some ordinary language of finite words. And then I'm going to talk about the limit closure of that language by saying, I'm going to take the infinite word such that it's not true that every prefix belongs to W, but for every n, I can find a longer prefix that belongs to W. Okay, not every prefix belongs to W, but no matter how long I go, maybe I'm not at a prefix of W, but if I go a bit further, I will find some prefix that belongs to W. Okay, so for infinitely many n, there are places I can cut it off where the word is in W. So a word is going to look like this. There's my alpha. And then somewhere here, I can cut it off. And this will be in W. And I can cut it off somewhere there. And this will be in W. So it's not true that every single place I cut it off, I'll get a word in W. But wherever I look, somewhere along the line, I can cut it off and get a word in W. Okay, and this goes on forever. And now the theorem. An omega regular language is recognizable by a deterministic Bucci automaton if and only if there is a regular language W. So an omega regular language, let's call it L, is recognizable by a deterministic Bucci automaton if and only if there is a regular language W such that L is the limit closure of W. Okay, so once you've seen this proof I did just now, you won't have any trouble doing this one. So what's so great about deterministic Bucci automata? Well, you can see they're rather limited. So if they're going to be limited like that, we hope to get some payoff. So deterministic PA are closed under complement. So let me say that more precisely. If A is a deterministic Bucci automaton, there exists an NBA A prime such that the language of A prime is equal to the complement of the language of A.
Maria has a question.
Yeah.
She would like to verify if the set of limit points of a limit language must be finite.
What are limit points?
So I guess that the limit points, I mean like the strings that words converge to. I don't know if that makes sense.
So it doesn't make sense as you've stated it, but there is sense in what you're saying. One has to work a little harder to make that a precise statement, but I think the short answer to your question is no.
Okay.
But now I'm a bit afraid that I've told you all this because I can see you going off and studying the topology of Omega languages. Not, but I mean, it's a great entertainment. But so clearly that was a topological argument, right?
Yeah.
And there's some topology going on, which I don't remember, but it has been studied. And you can actually study exactly what kind of, but the thing is, these are not simple things like closed sets or open sets.
Yeah.
I believe they are G deltas.
So they are Borel.
Yeah, definitely they're Borel. In fact, there is a whole subject called Borel automata, which recognize languages up the Borel hierarchy. So you change the acceptance condition and make it more complicated.
Okay.
Yeah, but come, let's get back to our day job. So this is a lot of fun. Okay, let me try and prove this quickly. So how do we construct A prime? So actually what I said here is not strictly correct, because literally to say closed under complement means the complement is also a deterministic automaton. And it's not the case. The point is, for a deterministic automaton, you can easily construct its complement as an NBA. For an NBA, you can also construct the complement as another NBA, but it's a lot of pain. Maybe takes like 2 whole lectures just to explain that construction. So a number of things still work. Determinization absolutely doesn't work. And strangely enough, I've not studied minimization for Omega-automata. So I know nothing about the status of minimization for Omega-automata. Anyway, A prime, how am I going to define it? Whereas, of course, the original A, I'll just use these letters, Q, sigma, same sigma meaning same alphabet. Now, the new machine is going to have this state space. So it's going to have basically more or less 2 copies of the state space tagged with either a 0 or 1. Right? Q0 prime, the start states of the new machine are same as the start states of the old machine, but tagged with a 0. So you're going to, so there's kind of 2 sectors for this machine, a 0 sector, which is just an exact copy of the first machine, and a 1 sector, which is also more or less a copy, except that all the except states have been removed. And now I'm going to describe the transitions of A prime. I'm going to use the arrow notation. So S0 can take an A and go to S prime 0 if delta SA equals S prime in the original deterministic thing. S0 can take an A and go to S prime 1 if delta SA equals S prime in the original machine. And S1 can take an A transition to S prime 1 if delta SA equals S prime in the original machine. Okay, so what does this machine do? It's reading a word and it's staying in the 0 sector. And at some point it says, I'm jumping to the 1 sector. Okay, I'm jumping to the 1 sector. And once it's in the 1 sector, it can never get out. And by the way, over here, I have to say S prime is not in F. Otherwise, obviously, I can't jump to that state. So at some point you see, I have a transition to a non-accept state. Let me jump to it and change my label from 0 to 1. Once you're in the 1 sector, you can only do these transitions.
Maya has a question. She asked if for the union on the top, if it shouldn't be Q remove F times 1.
Yes. Sorry. Thank you. Yes, thank you. So what does this machine do? At some point, it jumps to sector 1 and stays there. Now it might be that in the old machine, you're in a state that's a non-accept state, and you have a transition to an accept state. So then you just don't put that transition in here, and the machine jams. So what are the accept states of the new machine? It's any of the states in sector 1. So how does this machine accept? It says, okay, at some point, if I'm going to hit an accept state of the new machine, I better jump to sector 1, because that's the only place where I'm going to find accept states. So once you jump there, you're guaranteed that you're never hitting the accept states of the whole old machine. So you're exactly getting the complement of the old machine, of the language of the old machine. Okay. So complements of NBA can also be done but it is very hard to describe. Well, not impossible to describe. I mean, I could have described it to you if we were willing to spend like 2 whole classes on it, but I'm not. Uh, so let me wrap up with just some remarks. I get to go to 12:55, right? So there are various other acceptance conditions considered. So these are typically have the names of the people who invented them attached to them. So one is Rabin, another one is Street, who really does spell his name with 2 T's. Mueller. Michael Rabin, by the way, is a famous, ultra famous Israeli computer scientist. He invented the theory of NFAs. So he and a fellow student, Dana Scott, were undergraduate summer interns at IBM, and their manager basically left them alone and didn't give them anything to do. So they started reading, this was in 1956, they started reading existing papers on automata theory, which was always couched in terms of DFA, and they invented NFA and proved the determinization theorem. Later on, they won the Turing Award for that work. Rabin has also done other fundamental things in automata theory. He went and invented probabilistic automata and proved that probabilistic automata, if you define the notion of acceptance the right way, accept non-regular sets. But anyway, he also defined a certain class of Omega-automata with a different acceptance condition, and so did Street, and so did Mueller. And with these, with some of more complicated acceptance conditions, so it's not just one set of accept states, but multiple sets of accept states, and complicated things like you must hit all the accept states in this set or all the accept states in that set, and so on. So more and more complex acceptance conditions. But with these various conditions become easier to prove. So for example, deterministic Mueller automata recognize all omega regular languages. So you get kind of a more civilized theory in terms of what you can and cannot do, determinization and so on, but at the price of much more complex acceptance conditions and much harder to reason about. So we won't go into all these things. When I teach Comp 525, I usually do a little bit. I usually do Müller-automata, and usually lots of people like to do term papers on automata theory. So I remember one person wrote a term paper about, I guess, 10 years ago on the topology of the sets accepted by different kinds of automata. And there was a whole family of different acceptance conditions that exactly corresponds to the Borel hierarchy. So that's it for Omega-automata. They will crop up again when I talk about linear temporal logic tomorrow. So I will end the class here. I'll stay on for a few minutes in case anyone is interested in asking any questions. And maybe. Yes.
Oh, can I ask a question about the homework, just to settle my soul about it?
Can you turn on your camera so I can see who you are?
Yeah. Should be on. Oh, there we go.
Evan.
Hi.
Hi. Where are you?
Rochester.
And do you have strobe lights in your room?
No, that's a fan.
I see. Okay. I thought we were meeting in a disco or something. All right. Very good. Okay, so perhaps you should turn off the camera because I'm getting dizzy looking at that.
Sorry, I don't want to give you what's it called? A stroke or something.
Like seizure.
Right.
Yeah, that's better. Thank you. Okay, what's the question?
Right. So for number 10, was it that we were supposed to give a specific example for a specific n, or prove it
theory.
for all n?
How can it be for all n?
Well, I did it for 7-up.
Okay, yeah, you can possibly do it for 7-up, but I said, give me an example of an automaton.
Well, I did a bit of both.
Well, sort of bit of both. You're reading the wrong damn quantifier. I said, give me an automaton. That's an existential quantifier. When I ask for an existential, I want an example.
In real life, there's such thing as.
Don't fucking tell me about real life. It's one example. That's all I want.
I'm sorry. But also,
crazy when people read the wrong quantifier.
Also, can we resubmit by midnight?
Has it stopped accepting?
No, I don't think so.
So I'll check what I set it for. If I haven't set it for midnight, I will change it to midnight. I thought I set it for midnight, but you know, I find my course is very mysterious.
I think
so,
it's set to midnight.
Sorry?
It is set to midnight.
Oh, great, great. Okay, so yes, you can submit to midnight.
Okay. Just because I want to get number 7 so bad.
Number 7 is difficult. You know, I said I would put some difficult questions.
Can I ask something about number 7?
Sure.
Like, I'm feeling very dumb. I went to the office hours and asked, and then I got a hint, but still couldn't make it. So can I just kind of sketch the idea that I have, and can you tell me if it makes any sense or not?
Well, I'll listen. I may refuse to answer though.
Okay. So according to what I got in the office hours, I basically need to look at the exponential as a logarithm. Mm-hmm. But then I'll have to deal with a lot of intermediate states.
Yeah, as long as it's finite.
And then every time I do induction in, let's say, k+1, I'll be moving not really one, but the step that I'm making is in a logarithm basis. This
It's
is this the
exponential.
intuition?
It's exponential.
Sorry, exponential basis. Is this the intuition for this problem?
Yes, but you know, that intuition anyone can tell you. We still want to see how do you do that. I mean, I won't give you any credit for telling me that, because that's kind of
Right.
just describing what you have to do. The trick is, how do you do that?
Right. I'm still thinking about it. I think I won't get this question at all because I'm stuck since Friday.
Well,
But
if it makes you feel any better, I didn't get it either.
okay.
However, my wife actually did get it, so I know it's possible. And since then, I've seen a slicker solution by Dexter. So, but you have to think outside the box, outside many boxes. And if there's one hint I can give you, I will say, think about matrix multiplication.
All right, thank you.
All right. Thank you. I'll give it another
But
thought.
you know, it's not your sacred right to get every problem. Some things are beyond.
That's fair.
So when I normally teach Comp 330, in every assignment, I give a question called spiritual growth. And I say, this question will not give you any credit for the course, but it'll make you feel great if you solve it. And this one I have given. So I've taught Comp 330 for, I think, maybe 14 or 15 years. And I think in 14 or 15 years, 2 people did it. So that should give you an idea. It's not like, yeah, well, you know, we work for the weekend and we'll just get it. Lots and lots and lots of very smart people didn't get it.
Because one very stupid idea that I had, like if I could have a structure that where I can carry more information, that's exactly what I need.
Yeah.
As you said, matrices or complex numbers, they're things that carry more information.
Yes. Good.
But still,
I'm listening. Yes. You need to carry more information. How do you do it? I don't know.
Yeah, like I would need to change whatever I have to have another plane or something like Cartesian plane.
I don't know about the Cartesian plane analytica. It is more like you have to carry an auxiliary thing.
Yeah, okay. I'll give it a thought. Thank you.
There's quite a lot to be learned from trying to do impossible things. Well, this is not impossible. This is possible, but it is hard. And I don't want you to feel like, oh my God, I'm failing if I can't do this one. That's crazy. So I know one person has correctly done it in an original way, not by Googling and finding the answer on the internet.
In this year?
Sorry, this year, yes.
Hmm.
So one guy in this class solved it immediately.
I want to guess Asa.
I'm not going to reveal all that. This is like violation of privacy to tell you that. But anyway, this is doable.
Wait, can I ask if it was me?
I don't know. I haven't seen your assignment.
Okay, because I figured it out, I think, but it has nothing to do with logarithms or matrix multiplication, so I'm not sure now.
There are different ways of presenting it. Does it have anything to do with binary relations?
Yeah, I guess I sort of use an equivalence relation at one point, kind of,
An equivalence relation.
but not really.
Okay, well, I will look at it, but probably not now. I'll have Michael look at it. But it doesn't, I mean, if you have successfully done it, then you're using ideas that I have not seen used before. So
Can I like describe the gist of it and ask if it makes sense?
Sure, go ahead.
So I took, so sort of the obvious way to do it is to let the set of states be, so you have a DFA that recognizes the language L, and its set of states is S. Sort of the obvious way to do it is to construct an NFA that recognizes log L, where it's...
One second, just 1 second. I'm trying to do something with my iPad, which requires fierce concentration. Okay, good. Excellent. All right, super. Thank you. Okay, we get out of here. I just wanted to make sure that these notes got sent. Yes, sorry, Isa, I wasn't listening. What? Can you start again, please?
Sure. So you take a DFA that recognizes L. S is its set of states.
Can you turn on
And
your
sort of
camera?
what?
Can you turn on your camera?
Oh, yeah.